Hi everyone. Thank you for watching my educational talk at this year's ISMRM. I'm a bit sad I cannot make the dad jokes about Sydney and Sydney, but I am hopeful for this to be another enriching year at this great conference. Today, I'll be talking about a few applications for RF pulse design. I'll close the video and we can begin. I have nothing to declare. To ease with viewing this video, I've tried to give a rough timeline of my talk for you to be able to fast forward to the parts of interest, although I do hope you'll try and watch the entire version. By now we are all aware of the relationship between image space and the spatial frequency domain K-space where data is collected. We also can recall the inverse relationships between spatial resolution and K-space extent, and vice versa. For some applications, we might want to image only certain regions within our object at a high resolution. With our K-space, image space relationships at hand, at first glimpse, we might think that we could simply downsample K-space, increasing delta K sub r and decreasing our imaging field of view. Yet, by now we also know that such approaches will result in aliasing artifacts, where signal from the object out of the desired field of view wraps around into our image. Therefore, we need an alternative RF excitation-based approach such as inner volume imaging. Inner volume imaging is also sometimes referred to as reduced field of view imaging. One of the first examples was by David Feinberg for spin echo imaging. Here, a slice or slab selective excitation pulse was paired with a slice selective refocusing pulse that was applied orthogonally. Only the intersection of the two pulses generates a spin echo, forming a selected inner volume. This idea was later expanded to zonal oblique magnified, or zoom, where the refocusing pulse pair was applied at an acute angle to permit multislice acquisitions. This was first done with an EPI readout for mapping the apparent diffusion coefficient of the optical nerve. A further approach for inner volume imaging is through 2D RF pulse designs. In this case, a specialized excitation K-space trajectory is needed to encode the RF waveform. This pictorial example shows a 2D inner volume target pattern and the spiral trajectory used for pulse design. Here are the RF and gradient waveforms used to generate the 2D excitation. Using a simple least squares pulse design, a reasonable excitation can be produced. The RF pulse is, however, over 12 milliseconds, which might be unsuitable for some applications. This type of spatially tailored RF pulse design can likewise be extended to 3D. Here, many variants of excitation trajectories exist, as highlighted by this graphic from Matthias Davids et al. Just to quickly show a few more examples of inner volume imaging, I'll first point to this one using zoom EPI in the spinal cord. In this case, T2 weighted and diffusion weighted images and apparent diffusion coefficient and relative anisotropy maps were acquired at 3 spinal locations. In this example, an EPI trajectory was used to generate 2D RF inner volume excitations with separation between water and fat profiles. This was used for single-shot diffusion imaging of the cervical spine. Another common use of inner volume imaging is with spectroscopic imaging techniques such as point resolve spectroscopy or PRESS. In PRESS, a slice selective excitation pulse is followed by 2 180-degree refocusing pulses to localize a single voxel. In this final inner volume imaging example, we look at a 3D case. In Figure A, the full field of view image is shown of a corn cob. In both B and C, an inner volume excitation is performed to image a single kernel, yet C is accelerated. In the inner volume image Figure D, the same measurement time as B was used, yet with over 15 times higher resolution. Cases B through D all make use of an additional RF pulse method we will discuss later, called parallel transmit. Moving on, we will discuss the next RF pulse application, simultaneous multislice, or SMS. As the name suggests, SMS allows the excitation of multiple slices at a time, which decreases acquisition times. Unlike parallel imaging methods that reduce phase encoding steps to accelerate imaging, SMS does not have the same SNR penalty, nor changes the readout time, which is an important thing for EPI acquisitions. A pictorial example of SMS is shown here. On the left, we have a classic slice-select-Chenard-Leroux RF waveform. On the right, we have the simulated slice profile of the pulse using a typical trapezoidal slice-select gradient that is not shown. While the previous pulse generated a slice centered at isocenter, we can also apply a linear phase term to the complex RF waveform to excite a slice at a different location. Recognizing this, Muller proposed the idea of summing slice-selective RF waveforms with different linear phase terms to excite multiple slices, beginning the concept of SMS. As described, SMS leverages the Fourier shift theorem. Mathematically, we express the generation of SMS pulses as the following summation. In the classic form of SMS, the same slice-selective pulse envelope is used for all excitations. The number of pulses n that are generated is also known as the multiband factor. Also in the classic form of SMS, a common slice-select gradient is played out and the slice spatial locations are assigned as regularly done in slice selection and is shown in the exponential term. Despite being introduced over 3 decades ago, SMS only rose in popularity with the advent of parallel imaging using multi-channel receive arrays. In the top row of the figure, we see an example of a simple multiband factor 4 SMS excitation. Here, the received signals from all slices overlap. It is possible to disentangle slices if there is sufficient distinction in coil sensitivities along the slice dimension, albeit with likely G-factor noise enhancements. Slice disentanglement in the reconstruction is greatly improved with the concept of controlled aliasing and parallel imaging results in higher acceleration, or caipirinha, introduced by Felix Brewer et al. In the middle and bottom rows of the figure, the SMS pulses are employed with a schedule of phase cycles via caipirinha, causing a deliberate field of view shift in the superimposed images. In the ZY plots on the right side of the figure, we see that the caipirinha approach leads to alias pixels with unique origins in both the slice and phase encode directions, which will allow for an improved parallel imaging reconstruction with lower G-factors. SMS is a popular method for most applications where speed is essential. Here we show an example of a myocardial perfusion imaging study where the goal was to image the dynamic paths of a contrast agent using a multiband factor of 2. Figure A shows the superimposed slice images with field over 2 aliasing from the caipirinha method. B shows the corresponding disentangled slices. C shows the resulting G-factor maps, which still shows some noise enhancements. This paper uniquely describes the implementation of SMS caipirinha in a steady-state free precession sequence, where additionally RF phase cycling is used, so a careful phase schedule is planned to maintain steady-state behavior. SMS EPI has been a popular approach for fMRI applications, and typically higher multiband factors are used. In this example, a comparison is drawn between multiband factor 5 SMS EPI and a less conventional 3D EPI sequence. The acquisitions were matched for spatial and temporal resolution, and a variety of functional tasks were performed. Each column represents a different task activity where the average T-score maps for 10 volunteers are shown. Ultimately, it was found that the activation performance between both methods were very similar, although there are potential SAR limitations to the SMS approach, as we will soon discuss. Finally, diffusion imaging commonly deploys SMS. In this example, a major advantage is shown for diffusion spectrum imaging DSI, which can have prohibitively long acquisitions. By using a multiband factor of 3, the DSI acquisition drops from 45 minutes to 15 with very similar reconstruction results. Aside from coil sensitivity and parallel imaging limits, there are 2 major factors that constrain the overall multiband factor of an SMS acquisition: the hardware limits of the RF amplifier and the safety limits of SAR deposition. Both scale proportionally with the multiband factor n, and it follows that peak RF power scales with the square of n. We can see this in the figure where a single slice RF waveform in black has a normalized peak amplitude of 1, and the multiband factor 3 pulse generated with a single slice waveform has a peak amplitude of roughly 3. One approach to combating peak RF amplitude hardware limits of SMS has been to add additional phase offsets to each slice. The phase offset term shows up in our multiband RF pulse equation in magenta. In an ISMRM abstract in 2012, Eric Wong reported an optimized set of phase schedules to reduce peak amplitude of SMS pulses for a given multiband factor. In this example, we see the peak amplitude reduced by about 1/3 when using the optimized phase offsets. A few other approaches that explicitly minimize peak RF amplitude of SMS pulses are root flipping and time shifting. In the top figure, the root flipping approach by Sharma et al. Highlights how the passband roots of individual bands of a multiband pulse can be arranged so that they do not overlap and contribute to a larger RF amplitude peak. In the bottom figure, the root flipping method is compared to optimized phase scheduling, as well as time shifting plus phase scheduling from Orbeck et al. For the same peak RF amplitude, the root flipping approach yields the shortest RF pulse duration. Meanwhile, other SMS methods more directly address the increased power deposition with multiband imaging. The power independent of the number of slices or pins approach does this by convolving a conventional slice-selective RF pulse waveform with a Dirac comb function which generates a periodic series of slices. Unlike conventional SMS with constant slice-select gradients, pins pulses use small slice-select gradient blips whose area determine the period between pin slices. The turning on and off of gradients, or discrete excitation case-based sampling, is what reduces the RF power deposition. Nevertheless, the pins approach does create an infinitely wide field of view in the slice dimension, which might limit its applicability to some applications. Our recent work in SMS pulse design faced hardware and power limitations by directly addressing them during pulse design with constrained optimization. In this example, we designed small tip angle multiband pulses with the goal of minimizing the out-of-slice ripple that is a common trade-off with slice selection. The optimization has direct constraints on RF peak amplitude, integrated pulse power, which is proportional to SAR, and in-slice excitation error. When SMS is posed as a 1D pulse design, so only along the slice dimension, this optimization with multiple constraints is computationally feasible for online pulse design by using semi-definite programming methods. The next RF pulse application we will discuss today is RF or B1 shimming. Inhomogeneity in the RF transmit field B1+ is a problem that is especially seen with higher MRI field strengths. This is due to the decreased RF wavelength with increasing frequency. When the RF wavelength is shorter than the object being imaged, constructive and destructive interference patterns occur that cause spatial flip angle non-uniformities. For the head, this occurs at 7 Tesla and above, but for the body, this even occurs starting at 3 Tesla. The left-hand picture shows an early brain imaging example comparing 4 Tesla at 170 MHz and 7 Tesla 300 MHz. The 4 Tesla experimental image and B1 field are much more uniform compared to the 7 Tesla example. Before we can begin to discuss B1 shimming for B1 inhomogeneity mitigation, we must discuss the hardware differences required. B1 shimming and its more sophisticated counterpart pTx both require specialized coils with independent parallel transmit channels. Unlike conventional single transmit MRI, where a single RF waveform is played out in quadrature using a birdcage coil, parallel transmit coils deliver individual RF weights or waveforms through independent transmit channels. While there are a few commercially available parallel transmit coils, many of them are constructed in-house by researchers. For further information about the validation and safety aspects of an in-house pTx coil, our digital poster, ISMRM number 4038, reviews this process. Using these dedicated parallel transmit coils, we can generate the channel-specific complex transmit field sensitivities shown here. These are used to perform B1 shimming, which is considered the simplest form of parallel transmit or pTx. These independent channels are used in conjunction to create the combined excitation pattern. Here on the right, the channels are combined with equal weights producing the equivalent of a single transmit excitation. B1 shimming is also referred to as static pTx because the B1 shimmed RF pulse is constructed of the same temporarily varying RF waveform. Each transmit channel has a unique complex weight W and spatially varying transmit sensitivity S of R, which is also known as a B1 map. This figure demonstrates B1 shimming compared to conventional single transmit. In a parallel transmit coil, Single transmit pulses can still be obtained by setting equal weights to all channels in quadrature phase. This is shown on the left and is commonly called circularly polarized or CP mode. On the right, we show an example of B1 shimming. Although the same RF waveform is used, it has distinct amplitude and phase values compared to the CP mode. In this GIF, we now show the single channel contributions with those same B1 shim weights on the left and the combined shim solution in the center. This can be contrasted to the equivalent CP mode excitation on the right. As you can see now in the final B1 shimming that is frozen, there is slightly less inhomogeneity in the combined RF transmit field when using B1 shimming, especially, for example, in the top left region of the brain slice. Nevertheless, sometimes with B1 shimming, only modest mitigation of the non-uniform B1 field can be achieved. This now motivates the need for full waveform parallel transmit, which has additional degrees of freedom by employing unique temporarily varying RF waveforms per each independent transmit channel. pTx is not only useful for improving B1 inhomogeneity, it can also be used to accelerate RF pulses and even enable increased control over power deposition. We revisit our same GIF-based example one final time using full or dynamic pTx. Again, the individual pTx waveforms are found on the left, and the combined full pTx solution is in the center. Freezing upon the full pTx excitation now, we can appreciate the substantially improved B1 transmit homogeneity even compared to static pTx or B1 shimming on the right. As I also mentioned, pTx can be used as a mean of pulse acceleration. This was described by Ulrich Kascher et al. As transmit sense, in which the analogy was made to sense parallel imaging methods, but in this case, excitation K-space is undersampled. In this example, we compare single transmit in the top 2 rows to parallel transmit with 8 transmit channels in the bottom 2 rows. The RF pulse is exciting a 2D inner volume with a spiral trajectory, similar to what was shown previously. Using pTx, the over 12 millisecond pulse length in 1Tx has been reduced 4-fold. It is important to note that the pTx pulse was designed without hardware limits in mind. This figure compares the excitation patterns for single and parallel transmit for that same inner volume excitation compared to the desired target pattern on the far left. For a sufficiently long pulse and spiral K-space trajectory, and also assuming no relaxation, the single transmit pulse reproduces the target excitation reasonably well. When the excitation trajectory and pulse length are reduced by a factor 4, the single transmit pulse cannot adequately generate the inner volume excitation. However, the pTx pulse on the far right can. A presentation on pTx would not be complete without discussing power deposition and SAR. The summation term in our generic pTx waveform formula leads to more complex electromagnetic field behavior and necessitates careful SAR monitoring. This is shown, for example, by the SAR simulations across 3 body models where a local SAR hotspot is generated that is asymmetric. Even still, one can also argue that the control over the superimposed electromagnetic fields provided by pTx can actually lead to better power management. The specific absorption rate generated by a pTx pulse is dictated by the spatial electric field components. With a single vectorized pTx RF waveform X, the SAR is computed using so-called Q matrices introduced by Ingmar Gracelin et al., which are comprised of the spatial E-fields averaged over a typical 10-gram volume and the associated conductivity and mass density of that tissue volume. Based on the object model used for these electromagnetic field simulations, there could be on the order of hundreds of thousands or millions of Q matrices. Hence, a method to reduce this SAR computation was introduced by Gabriel Eichfelder et al. And is known as virtual observation points or VOPs. This method clusters volumes based on the eigenvalue decomposition of the positive semi-definite Q matrices and ensures that the worst-case local SAR will always be overestimated. VOPs need not be spatially contiguous, as shown in the 2 example figures. On the left, 2 total VOPs are generated, and on the right, 11 are. The 2 VOP example will be more SAR conservative, while the 11 VOP example will be less. I'll now review some popular pTx RF pulse design applications, and the first is slice selection. As we've already mentioned in this talk, conventional 2D imaging RF pulses only use a slice select gradient. To improve the in-plane homogeneity of the slice, fast KZ, or more commonly spokes, have become popular for pTx slice selection. For an axial acquisition, slice select RF subpulses with KZ slice select gradients are interleaved by gradient blips in the KX-KY plane. This produces a 3D excitation trajectory that has long KZ spokes sampled at a few KX-KY locations, often K-space center, and one or two others. This early example of pTx spokes by Cow and Setzenpop compares single transmit birdcage excitation to B1 shimming and two pTx spokes at 7 Tesla. While the B1 transmit field is much more inhomogeneous here compared to more modern 7 Tesla systems, it is easy to appreciate the uniformity one can gain when adding B1 shimming and especially full pTx with spokes. For 3D imaging, one popular pTx pulse design method is known as KT points. In this case, RF hard pulses are played out while interleaving excitation K-space is sampled at discrete 3D KT points. The figure shows the single transmit equivalent CP mode excitation in the top row A and the KT points pTx acquisition in the bottom row B for a GRE flash sequence. The left column is proton density weighted and the right is T2 star weighted. Both 2D spokes and 3D KT points trajectories have gained popularity not only for their effectiveness, but also because of their relative design simplicity. Because the spatial B1 field is unique for each object and positioning within the scanner, pTx pulse design is often limited to online design only. In both spokes and KT points, the full RF waveforms are not optimized, but rather the relative slice select or hard pulse subweights. To overcome the computational burden of online pTx pulse design, a newer promising method for parallel transmit is the universal pulse. Universal pulses are generated by optimizing pTx waveforms over a population of B1 and even B0 field maps. The assumption is that the population adequately represents the B1 and B0 variation that one might observe in an individual. While a universal pulse would almost certainly not perform as well as compared to a subject-tailored RF pulse, the universal pulses have proven to greatly outperform single transmit and B1 shimming. Hence, it can be said that universal pulses are a special type of calibration-free pTx. Currently, universal pulses have mostly been created for 3D imaging sequences. Parallel transmit can also be integrated into other RF pulse design applications we've discussed today. For example, in this paper by Ben Poser et al., they combined pTx with SMS. The interesting result here is that in the SMS pTx approach, the transmit sensitivity of the coil is exploited such that the total SAR is less than the single transmit equivalent. I've already given some previews that pTx can also be used for improved inner volume imaging. Matthias Davids et al. Used pTx to create a 3D cube excitation. In the pTx pulse design, they also included gradient optimization and introduced B0 robustness with off-resonance terms in the design system matrix. Here we show one of the 3D trajectories, a stack of spirals, which produced a pTx pulse cube excitation that varied between 2.9 and 4.9 milliseconds based on the trajectory optimization. One final pTx application I'll leave on harks back to the idea of better or safer SAR management with pTx. Because we do have control over the superimposed electromagnetic fields, methods have been introduced to create implant-friendly pTx excitations. For example, this can be useful even at lower field strengths when neurological devices like deep brain stimulation or DBS electrodes would normally prohibit MRI scanning due to RF heating concerns. In this paper, Yijik and Ariatman et al. Used parallel transmit to create so-called implant-friendly modes where null or reduced electric fields with reduced B1 plus perturbations are generated around DBS lead tips. This is demonstrated with the SAR simulations of the DBS leads on the left. In addition, B1 homogenization with pTx was optimized based on these implant-friendly modes to also obtain a uniform excitation pattern as shown in both phantom and human brain body model simulations on the right. In conclusion, Today I've reviewed RF pulse applications of inner volume imaging, simultaneous multislice or SMS, B1 shimming, and parallel transmit or pTx. pTx can also be used to enhance the other mentioned applications by offering further degrees of freedom with the RF pulse design. While not all applications or examples of these methods were discussed today, I encourage you to begin further reading if you wish by checking out some of the journals that I've included in my Zotero reference group at the shortened URL listed on the bottom of the screen. I would also recommend exploring some of the RF pulse design sessions at this year's ISMRM for the latest breaking techniques. With that, I'd like to thank my colleagues in Glasgow, Scotland for their support as I prepared this educational talk, and I'll look forward to chatting with you at the live Q&A session. Thanks.